Welcome to the lecture series on numerical methods. In the last lecture, I have discussed about numerical integration based on trapezoidal rule. So, this lecture I will just continue this error approximation for this trapezoidal rule here. So, in the trapezoidal rule, if you will just go for this error calculation, then we can just write this error as in the form of like as I have told you that if you will have like 2 points only, that is B and A, and we will have a single interval there, then we usually are just expressing this error term as in the form like R of f x. This should be less or equal to B minus A whole cube by 12 f double dash of x absolute values, that is a maximum of x lies between A to B here. We have just considered this positive value since we have just taken here absolute value in the left hand side here. So, if you just go for this expression for a composite formula, this is for like a single formula. If you will just consider this formula in the form of A to B f of x and dx, and h is a suppose only one interval we are just using, then we are just using this formula, that is in the form of b minus a by 2 f of a plus f of b there. But in a composite form, if we are just expressing this formula, then n intervals, if this interval a b is subdivided a to b, x0 x1 to xn here, each is of like equal spacings, these points are situated. So, usually we are just defining this xn minus x0 by n, this as h, we are just defining this one. So, that is why we will have these intervals like x0 to x1 f of x dx plus x1 to x2 f of x dx plus up to xn minus 1 to xn f of x dx here. And then this formula is directly can be written as h by 2 f of x0 plus f of xn plus 2 into f of x1 to f of xn minus 1. So, in each of these intervals, if you will just see here, we will have a error term, we will have a error term, we will have a error term. Since whenever we are just approximating this curve bounded area there, so each of this region that is approximated by a trapezium there. So, that is why in each of this trapezium we will have a error section either in the lower side or in the upper side. So, that is why if you will just consider this total area for this composite formula here, that can be written as R of f of x, this equals to, obviously this formula is written in the form of minus h cube by 12, and each of this error like first term, if you will just the error is f double dash zeta, second we will have this error like zeta 1 f double dash of zeta 2, up to the last section we can just this write this error as f double dash of zeta n suppose, where we can just write this zeta I is the error which is lying between xi minus 1 to xi here, I equals to like 1 to up to n there. So, if you will just go for this error bound, then we can just write R of f of x, it should be less or equal to h cube by 12, and if you will just find a maximized term or the maximized error term from this one, or we can just consider each terms of the error are of equal value, or we can just consider this maximized error term there itself, then we can just take the total sum as n here into f double dash of x here, which can take a positive value here, since we are just taking the absolute value on the left hand side. So, we can just take this absolute value that is f double dash of x here also, where x should be lies between a to b here. That can be taken as the maximized value of f double dash x within that range here. So, we can just write that one as a maximum of x which should lies between a and b and can be taken by the second order derivative there. And in a complete form, if you will just write this formula, this can be written as n hq by 12 maximum of f double dash of x, where x should lies between a to b here. And sometimes also if you will just replace nh equals to b minus a, then you can just replace this formula, that is h square into b minus a by 12 into maximum of f double dash of x there. So, that I have just written here also, that is nhq, nh equals to b minus a. So, that is why this can be written as b minus a whole cube by 12 n square also sometimes we can just write, and maximum of f double dash x. And this above expression shows that the increment of number of intervals gives less error, if you will just see, in comparison to the earlier one. If you will just see total interval, if you will just take a single step of composite rule, then we will have a larger error. If you will just subdivide each of these sections, then we can have less error there itself, since in each of these intervals if you will just see, this error will be reduced there, and that is why we can just use this composite formula to get a better result. In geometrical interpretation, if you will just see here, in each section if you will just see, this error is getting reduced here, but in total section if you will just see, this error is very large compared to this lower graph here. That is n number of trapezoidums with width is with ordinates f xi minus 1 and f of xi, if you will just consider in a geometrical way, then the sum of approximation of the area for this curve y equals to f of x above the x axis and ordinates x equals to a and b gives the maximized areal cross section under this curve there. Then if suppose a question is asked like evaluate integration I equals to 1 to 2 1 by 5 plus 3x into dx with 4 sub intervals using trapezoidal rule, and compare with exact integral and find the absolute error and find the bound for the error. If you will just see here, your a is given as at 1 here and b is 2 here, 4 sub interval means n equals to 4 here. So, this integration is given as I equals to 1 to 2 1 by 5 plus 3x dx here with 4 sub intervals. This means that with n equals to 4 here, and if n equals to 4 here, so then we can just define h equals to b minus a by n here. So, that is 2 minus 1 divided by 4, that is 0.25 here. And if we have just defined h equals to 0.25 here, the nodal points, it is just starting from 1, 1.25, then 1.5, then 1.75, then last point is 2 here. And corresponding f values, you can just define that one as like f of x is given as here 1 by 5 plus 3x here. Corresponding values for x equals to 1, we can just get f of x as 0.125. For 1.25, we can just get 0.11429. 1.5, we can just get 0.10526, 0.09756, and 0.09091. Now we will just go for this integration. So, this trapezoidal integration IT can be written as h by 2. So, we can just write 0.25 by 2 f of x0 is given as 1 here and xn is 2 here. So, f of x0 it is written as 0.125 plus 2 into 0.11429 plus 0.10526 plus 0.09756 plus 0.09091. So, this will just give the values as 0.10627, and exact value of this integration, if you will just go for this computation, we can just get 1 by 3 into ln of 5 plus 3x, if you will just see. And if we will just put this range 1 to 2 here, we can just obtain that one as 0.10615, and the absolute values, that is I exact minus IT here. In absolute form, if you just write 0.10615 minus 0.10627, this is 0.00012, it is very less here. And if you just go for this bound of this error, so absolute values, if you just consider, that can be written as error should be less or equal to b minus a h square by 12 maximum of f double dash x. If you just go for this error term here, so this error can be written as this should be less or equal to b minus a h square by 12 maximum of f double dash of x, x should be lies between 1 and 2 here. And if you just calculate this f double dash of x, we can just say this one as this equals to 2 minus 1 into h square is 0.25 square here by 12, and f double dash x, if you will just compute, that will just give you 18 by 5 plus 3x whole cube here, and this should be maximum value where x should be lies between 1 and 2 here. So, if you just see here, this function will achieve this maximum value whenever x equals to 1 there itself. So, if x equals to 1 there, then it will be 8 to the power 3 there, and its value is like 512 there. So, that is why we can just write this maximum value as 2 minus 1 is 1 here into 0.25 square by 12 into 18 by 512. This will just give you this maximum error term for this composite trapezoidal rule, that is just coming as a 0.0000180 here. So, then we will just go for 1 by 3 Simpsons rule here. So, whenever we will calculate this area of this curve bounded by this x axis, and if this area is approximated by this a parabola here, then we can just obtain this 1 by 3 Simpsons rule here. Especially we are just dividing this interval, like in the earlier case we have just divided into 2 points there, only single interval we have just considered. Here we will just subdivide this interval into 2 parts here, considering this middle part as a plus b by 2 there. So, if you just like divide any interval like a to b here, like 2 intervals, 2 sub intervals here, then we can just write this midpoint as a plus b by 2, and we will have 3 points like a, f of a, and like a plus b by 2, f of a plus b by 2, and then the third point b, f of b here. And we can just write this space size h equals to b minus a by 2 here, with x0 equals to suppose a there, x1 as a plus b by 2, and x2 equals to b there. So, if you just see in this slide here, you can just find that this paraboloid section, this is just approximating this aerial cross section that is bounded by this x axis and the curve there. So, if you just consider these points like x0 and f of x0 is the first point and x2 f of x2 is the last point here, then the middle point is denoted as x1 f of x1 here. So, this means that we are just approximating the 3 points of this curve y equals to f of x by a parabola joining these points p, q, r there, and this parabola is approximated with this curve is of degree 2 there. So, if this is approximated by a polynomial of degree 2, then we can just use Newton's forward difference formula for a quadratic polynomial by considering these points x0 f of x0, x1 f of x1, and x2 f of x2. If you will just write this Newton's forward difference formula for degree 2, so f of x can be written as f of x0 plus p delta of f of x 0 plus p into p minus 1 by factorial 2 del square of f of x 0 here. Since this function is approximated by a polynomial of a degree 2, the higher powers will just give you the 0 values there. So, in terms of x, if you will just write, since we have here 3 points like x 0 equals to a, x 1 equals to a plus b by 2 and x 2 equals to b here. If you will just rewrite this formula here, then this can be written as f of x equals to f of x 0 plus x minus x 0 by h delta f of x 0 plus x minus x 0 by h x minus x 1 by h 1 by 2 factorial del square f of x 0. And if you just use this integration like a to b f of x dx here for Newton's quadrature formula, a to b f of x dx, this can be written as x 0 to x 2 f of x 0 dx plus x 0 to x 2 x minus x 0 by h f of x 0 minus, sorry, this is a f of x 1 minus f of x 0 into dx plus x 0 to x 2 x minus x 0 x minus x 1 divided by 2h square del square of f of x 0 into dx here. So, first point, if you will just integrate, then you can just get x 2 minus x 0 f of x 0 here. Second point, if you will just integrate here x minus x 0 whole square by factorial 2, h will come out. So, f of x 1 minus f of x 0. So, that is why it can be cancelled out like a x 2 minus x 0 if you will just take, that will just give you 2h there. Since we are just approximating here x 0, x 1, x 2 here. So, each is of space h here, equispaced points we are just considering. So, that is why we can just write x 1 equals to x 0 plus h and x 2 as x 0 plus 2h here. So, if you will just integrate, then in the final form, if you will just put all these values here that we have just derived here, that is x 2 equals to x 0 plus 2h, x 1 equals to x 0 plus h here, we can just obtain that one as h by 3 f of x 0 plus 4 f of x 1 plus f of x 2. So, just a simplification if you will just do, then you can just obtain this formula. And directly also we can just write, since h is expressed here, that is as b minus a by 2. Since if you will just see here, h is nothing but b minus a by 2 here, since n is 2 here. So, that is why we can just write h by 6, or sorry, this is as b minus a by 6 f of a plus 4 f of a plus b by 2 plus f of b here. In terms of a and b, if we want to write this formula, so this can be represented in this form here. This is called 1 by 3 Simpson's rule. And if you just go for this error calculation of this Simpson's rule, we have to consider that this function is exact for polynomials of degree 0, 1 and 2 there. This means that it can just provide us the exact value. This means that this integration minus this formulated value, whatever this formula we have derived here, this difference will be 0 for 1 x and x square. This gives the exact polynomial of a degree less or equal to 3 here. So, for degree 4 we can just get exactly this error term for this function here. If you will just put here f of x equals to 1 for this error approximation, that I can just say that r of f of x equals to 0, like our earlier calculation. If you will just see, for f of x equals to 1, if you will just put a to b 1 into dx here, that is for f of x equals to 1, if you will just write this error term here, r of f of x, this can be written as like a to b 1 into dx minus your formula, that is as b minus a by 6. So, f of a plus 4 f of a plus b by 2 plus f of b. Then if you will just write this one, that is 1 plus 4 plus 1 here, this will just give you 0 value. Similarly, if you will just consider here f of x equals to x, suppose r of f of x can be written as a to b x dx minus b minus a by 6. So, first term if you will just write here as a plus 4 a plus b by 2 plus b here. So, this will just obviously gives you also a 0 value. Similarly, if you will just consider f of x equals to x square, this can also be written as r of f of x here a to b x square dx minus b minus a by 6 a square plus 4 a plus b by 2 whole square plus b square here. This will also give you 0 value here. If you will just consider like f of x equals to x cube, since directly if you will just put like the polynomials of a degree or 3, x is less or equal to 3 here, exactly 3 should be the error term here, but especially for degree 3 we are just getting 0 value here. So, that is why we have just to consider the immediate next term for this error here, that is f of x equals to x to the power 4. If you will just put here f of x equals to x to the power 4 here, that can be written as c equals to, if you will just see here f of x x cube, r of f of x equals to 0 here, and for f of x equals to x to the power 4 we can just compute c term here. So, that is a to b x to the power 4 dx minus, that is b minus a by 6 here, and your terms a to the power 4 plus 4 into a plus b by 2 whole to the power 4 plus b to the power 4 here. And if you will just like do some simplifications, we can just obtain this value as minus of b minus a whole to the power 5 by 120. So, then the total error term we can just write r equals to, or r of f x equals to c by n plus 1 factorial here, especially if you will just see, or p plus 1. So, c by 3 is your highest p term, since we are just getting for degree 3 also we are just getting the exact polynomial function which is approximated with this f of x value. So, that is why you can just consider p as 3 here, c by p plus 1. So, that is why 4 factorial here. So, f to the power 4 zeta value here, where zeta should be lies between a to b there. So, that is why we can just write, if you will just put here, that as minus of b minus a whole to the power 5 by 120 into 4 factorial f to the power 4 of zeta here. And this total term, that is just giving you here minus h to the power 5 by 90 f to the power 4 of zeta. The bound for this error, if you will just go for the positive values here, like modulus of r of f of x, this can be written as less or equal to b minus a whole to the power 5 by the total product, that is just coming as 2880 into maximum of f to the power 4x, where x should be lies between a to b here. Since Simpsons 1 by 3 rule gives us the exact result for polynomials of degree less or equal to 3, the method is said to be of order 3 here. That is why it is called 1 by 3 Simpsons rule here. So, as in the case of trapezoidal rule, if the length of the interval AB is large, then we can just find that B minus A is also large. So, the error term in expression 5 is also large. And in this case, the interval AB is subdivided into number of sub intervals of equal length, and we simply apply Simpsons 1 by 3 rule for each of these intervals to, or the sub intervals, to evaluate this integration, and it is basically called the Composite Simpsons rule here. Basically in trapezoidal rule we are this Simpsons trapezoidal rule, we have just considered a single interval there, and if you just go for this like your 1/3 Simpsons rule here, we have just considered 2 sub intervals there. So that is why from both these methods, if you will just compare like trapezoidal rule and 1/3 Simpsons rule here, then we can just visualize this error will be less in comparison to trapezoidal rule is larger compared to the 1/3 Simpsons rule here. This means if you will just use 1/3 Simpsons rule, we can just obtain these results maybe around 6 steps, then it requires near about 12 steps to get this result for this trapezoidal rule there. So the conclusion is that whenever we are just subdividing these domains into number of intervals, then we are just getting these results in more accurate form compared to the less number of division of the intervals. So in trapezoidal rule, if you just see, we have just used n equals to 1, and if we are just extending that word to n equals to 2 there, then this error is just getting reduced in the advanced form there. So that is why it is always impressive to choose this space sizes as larger to get this less error there. Thank you for listening this lecture.